Earlier in the course, we saw linear and nonlinear models for first-order differential equations. Now we're going to move to second-order differential equations, where our models will still be linear, but in some cases we'll be looking at initial value problems, and in some cases we'll be looking at what's called boundary value problems. The current set of videos is going to be focused on initial value problems. The first type of problems that we're going to consider are going to be spring mass systems. A spring has a natural length. Putting a mass on a hanging spring is going to stretch it a bit. And here in this diagram, S is the amount by which the mass is stretching the spring and holding it in an equilibrium position. And according to Hooke's law, the amount of force required to keep a spring stretched a certain distance from equilibrium is given by F is equal to Ks. What I've actually written is F equals K times the absolute value of S, because the force required to keep a spring stretched beyond or compressed within its natural length is the same. What's going to be happening with our spring and mass systems is that the spring and mass had been at equilibrium, and then it's going to be stretched or compressed below or above the new equilibrium position, and then either released with no initial velocity or with some sort of initial velocity. That'll set the spring in motion, and that motion is described by a differential equation, the solution to which is what we seek. It's the position function for the mass in the spring mass system. At the equilibrium position, so in B in this diagram here, the force pulling the mass down is due to gravity, and so we have mg is pulling down. That's just mass times acceleration. And the force, the restoring force that's pulling up through the spring is Ks according to Hooke's law. That gives us that mg minus Ks is equal to 0. Otherwise, it wouldn't be at equilibrium. This K that we see in the Ks expression is the spring constant. Part of our work is generally going to be to find that. For our work, we're going to assume that down is positive. That's an arbitrary choice, but it's what we're going to roll with. Assuming down is positive, if the mass is moving, so we have this situation here where the mass is off of equilibrium. The force acting on the spring is mass times acceleration due to Newton's second law. Well, I mean, it's not due to Newton's second law, but it's described by Newton's second law. Anyway, acceleration is the second derivative of position, and we're looking at position as being a distance from equilibrium. So our acceleration, A, is going to be d2x dt2. So for F equals ma, we have m d2x dt2, and that's going to be one side of the force picture here. The other side of the force picture is everything that's happening with the motion. And the mass had already stretched the spring s units from its natural length. And then for a spring x units from equilibrium, there's the restoring force of that spring. And the amount is going to be k times s plus x, but we said down is positive, and the restoring force is pulling the spring up. Therefore, that's a negative term, and it's being offset by mg, which is pulling down in the positive direction. So we've got that m d2x dt2 is equal to negative ks minus kx plus mg, and we already saw that negative ks plus mg is equal to 0. So those cancel each other out, and we end up with m d2x dt2 plus kx is equal to 0, and that's the differential equation that describes what's going on with the spring. I'll give a little caveat. This is for undamped motion, and nothing's actively pushing on the system. That said, we're going to solve this equation for every spring system for which this is a model. First, we're going to divide and substitute. If we divide this equation by m, then we end up with a term k over mx. And if we let omega squared equal that k over m, why omega squared? You'll see. That will yield d2x dt2 plus omega squared k is equal to 0. For which the auxiliary equation, I have a bit of an issue. We have m here that represents the mass. In our auxiliary equation, we keep using m for that. So I'm going to switch this to the auxiliary equation having r as its little variable in there. So the auxiliary equation is going to be r squared plus omega squared is equal to 0, which means that r is equal to plus or minus I times omega. That's square root. That's why we let it be omega squared. That's going to give us the equation of motion, which is what we were after, of c1 cosine of omega t plus c2 times the sine of omega t. That's the solution for every undamped spring system's differential equation, provided there's no forcing function. This is homogeneous.